Hello everyone. Welcome to the videos where I'm going to be going through all of the content covered in the handout that I've given you in class called Math 30-1, The Straight Poop. As you're familiar with this handout is not a series of practice problems. This handout is an extensive overview of all of the concepts we've learned in this course. So as I work through this, we're not going to be doing in these videos much, if any, actual math problems. What we're going to be looking at is just reviewing all of the content in the course so that at the end of this you can go to the handouts I've given you in class and attack those problems. One of the handouts I've given you is the one that has, I can't remember exactly, but around 300 different multiple choice numerical response questions. And at the end of watching these videos and going through this handout with you, you should, I hope, feel comfortable doing most, hopefully all, of those 300 odd questions. Once you've completed those 300 questions, you also have those 4 diploma exams, practice diploma exams that I've given you. Some are released exams from Alberta Learning, some are materials that I've put together, but they're structured based on the diploma exam that you'll be writing. Remember, with those 300 questions or so, those are multiple choice numerical response. Your diploma exam will also contain 3 written response worth a total of 25% of the exam. Many of those multiple choice numerical response questions could be turned into a written response question. And we've talked in class about what that means, about the necessity for you to explain things clearly, to algebraically show solutions if you're asked to follow those key directing words in the questions so that you get good marks on those written response. With that being said, let's get started. This first video is going to be Unit 1 and Unit 2 of the course. Unit 1 is Transformations and Radical Functions and Equations. This corresponds to Chapters 1 and 2. And we're going to start off with translation. So what a translation is a shift of a point or an entire function left or right and or up or down. And what happens is in the function we create a translation by changing the function y equals f of x to y minus k equals f of x minus h. So we have a replacement for x. X is replaced with x minus h, and we have a replacement for y, and y is replaced with y minus k. However, we typically don't write y minus k equals f of x minus h. What we typically write is y equals f of x minus h plus k. Just to review what the parameters h and k do, h is the parameter that's responsible for a horizontal translation, and whatever the absolute value of that parameter is, which means don't worry about whether it's negative or not, that's how far the horizontal translation is. On the other hand, the direction of the horizontal translation is indicated by the sign or the character or the nature of that parameter. If the character or sign or nature is negative, if h is negative, then the graph or the point shifts in a negative direction, which is to the left horizontally. And if the parameter h is positive, then you have a shift horizontally in a positive direction, which would be to the right. Same kind of deal going on with k. K is telling you a couple of pieces of information. It's telling you, first of all, how far the vertical translation is, and you simply look at the absolute value of the parameter. K is also going to tell you whether that translation is up towards the top or down towards the bottom of the page. And again, if the parameter is negative, the shift is negative. If k is negative, it shifts negative vertically, which is towards the bottom or down. And if k is positive, it shifts in a positive vertical direction. There's mapping involved here. And when I say that x maps to x plus h, what I'm telling you is what happens on the graph. I'm telling you that whatever h is, when you add it to the x coordinate, that's what the new x coordinate becomes. Notice there's no absolute values in that bottom line on the screen. If h is negative and we add a negative to x, then x will decrease, which is going to shift it to the left. If h is positive when we add it to x, then x will increase, which means it will shift to the right, following the rules. Similarly, it's y plus k for similar reasons. Bottom line is, in x comma y mapping to x plus h comma y plus k, you include negatives in h and or k if they are negative. I want to talk briefly about reflections. I'm not going to speak to parameters for reflections just yet. There are two types of reflections, generally speaking, in this first unit. There is a third one that we will get to, but there are two main types of reflections. One is horizontal, and a horizontal reflection is across the vertical axis. Just take a minute here and draw a set of axes on a piece of paper if you need to visualize this, and put a point someplace to the left of the y-axis. If I reflect that point horizontally, it's going to go across the y-axis, and it's going to be to the right of the y-axis. So a horizontal reflection is across the vertical axis. And then something that I know some of you still kind of struggle with, the equation of the y-axis is actually x equals 0. And again, if you've drawn a set of axes, and just take any point you want that's to the left of the y-axis, you will have a point where x has a negative coordinate. But when you put a point on the right of the y-axis, you will have a point that has a positive x coordinate, which means any place on the y-axis, x equals 0. You want to sort that out before the diploma exam. You don't want to get burned on something which, quite frankly, is kind of a basic idea, and it's not really a Math 30 idea. It's more a Math 10 idea or even a Math 9 idea. You don't want to get burned on that, so make sure you get it clear in your head. How do we get a function to reflect horizontally across the y-axis? What we do is we replace x in the function by negative x. So we go from y equals f of x to y equals f of negative x. By the way, the mapping is the same thing that happens in the equation. So we replace x with negative x in the equation, x becomes negative x in the graph. And by the way, when I say x becomes negative x, that just means it is multiplied by negative 1. So if x was 2, then it's going to map to negative 2. If x was negative 8, it's going to map to positive 8. This is a little different than the translations, because the translations had mapping that was opposite to the substitution. I just want to go back and show this to you. When we take a look at replacing, say, x with x minus h, what happens for the mapping is x becomes x plus h. So the mapping in translations is opposite to what happens in the substitution, whereas in reflections, the mapping is actually what happens in the substitution. Vertical reflections, by the way, are across the x-axis. So something that is above the x-axis reflected vertically will be below it afterwards, and anything below it, below the x-axis, will reflect above the x-axis. The equation of the x-axis is y equals 0. Again, make sure you sort that out. Y in the function is replaced with negative y, so this is what y equals f of x becomes. Y equals f of x becomes negative y equals f of x. However, if we multiply both sides of that equation by negative 1, we can write y equals negative f of x. So that's how you can recognize a vertical reflection. The mapping is that x comma y becomes x comma negative y. When we talk about invariant points are points that are on an original function, and after it's been transformed in some way, they do not move. So they're fixed. And in reflections, invariant points will happen whenever you have a point that's on the line of reflection. If it's reflecting across the x-axis, then any point above the x-axis goes below the x-axis, and any point below the x-axis will reflect above it. Well, that means that any point on the x-axis will not move. So for horizontal reflections, which are across the y-axis, the y-intercept of the function will not be affected. It will be an invariant point. For a vertical reflection, which is across the x-axis, any x-intercept will not be affected because it's on the line of reflection. I'm including now a third reflection, and we'll talk extensively about inverse functions, or inverses of functions rather, in a few minutes, but an inverse can be found by reflecting a graph across the line y equals x, so invariant points for inverses are points that are on that line y equals x. When we put all of this together, with the exception of the whole inverse reflection idea, we end up with this template on the right-hand side of your screen, which can be found on your formula sheet. Y equals f of x is translated, or transformed, I should say, into y equals a times f of, and then in brackets, b. Then there's another set of brackets which is crucial, x minus h, close brackets, plus k. Everything that we've learned about h and k are still true. And I'm going to talk about a and b here in a second, but before we do, you need to take care of these changes that the four parameters create in a certain order. Whatever changes happen due to a and b have to be taken first. Now, you can do a first and then b, or b first and then a. I don't care, and it doesn't matter, as long as a and b are handled before you start talking about h and k. What is the parameter a all about? Well, if a is negative, there's going to be a vertical reflection, and it's across the x-axis. If b is negative, then there's going to be a horizontal reflection, and that will be across the y-axis. The vertical stretch factor is the absolute value of a. So if a is negative 3, the absolute value of negative 3 is 3, the graph will be stretched vertically by a factor of 3, which means every point above the x-axis will now be 3 times further above, and every point below the x-axis will be 3 times further below. If a was 1/5, then the stretch factor would be 1/5, because the absolute value of a fifth is a fifth. That would mean every point above the x-axis would now be 1/5 as close to the x-axis above. And every point below would still be below, but it would be 1/5 as far below. You have to be careful with the parameter b, though, because b is not the horizontal stretch factor. We have to remember to reciprocate the value of b. And the absolute value is there just because we don't want to worry about negative for a stretch factor. So if b is 3, the horizontal stretch factor is not 3, it's 1/3. If b is 1/2, then the horizontal stretch factor is 2. Of course, there's a horizontal translation. We've already talked about determining whether it's to the left or to the right and how far it is. And there's a vertical translation, and again, we've already talked about that specific effect. We can put this all together in terms of this grand mapping scheme. If x is stretched horizontally by the reciprocal of b, then if we take 1/b times x, including a negative if b is negative, that will stretch x properly, and if b is negative, it will reflect it, and then we can add h. Similarly, a, including the negative multiplied by y, will reflect y if a is negative, and stretch the result, and then we add k. So there is a way to put this all together in, I guess, maybe more of an abstract fashion, and to say that the mapping is x turns to 1/bx plus h, and y turns to ay plus k. What is the inverse of a function? The inverse of a function is found by interchanging or swapping every x and y set of coordinates. So if 1, 2 is a point on the original function, you switch 1 with 2 and the new point is 2, 1. That means that this is a way to write the mapping. X, y turns into y, x. Be careful though, and I've mentioned this in class, that y, x, it's still an x coordinate followed by a y coordinate. That y in the y, x is the new x coordinate, and the x in the y, x is the new y coordinate. The result happens to be a reflection across the line y equals x, which means invariant points lie on this line. We've done this in class. There's an example. This might even be the example that we did in class. I'm not sure. But there's a function, and when we swap all of the x and y coordinates in each point, we get the inverse. It's useful sometimes to just understand that if you switch x and y, everything about x becomes true about y, and everything about y becomes true about x. So if I give you that blue function, and I don't show you the red function, or the red graph rather, which is an inverse, if I give you the blue function and I say, well, what is the domain of the blue function? Well, that's easy to see. You can see it goes from -6 to 2. If I say, what is the range of the inverse, you don't have to graph the inverse to know that the range of the inverse will be the domain of the original. Any intercepts that are y-intercepts on the original function will become x-intercepts on the inverse. Anything about x becomes true about y, and anything about y becomes true about x. To determine the equation of an inverse of a function, you switch x and y in the equation and then rearrange for y. Sometimes the inverse is not a function, and we use what's called the vertical line test to determine if the inverse is or is not a function. For example, that blue graph, which is an absolute value function, is an original function, and I have swapped all of the x and y coordinates, or I have reflected it across the line y equals x to get the pinkish graph, which is the inverse of the function. And that is not a function because a vertical line will cut the graph in more than one place. If I were to draw a vertical line here, you can see that that green vertical line intersects that pink graph in more than one place. What does that mean? It means the pink graph is not a function. So we have y equals f of x, and we have x equals f of y. But x equals f of y is not a function. Any function, we're talking an original function here, any function which goes up and down anywhere or in any fashion will have an inverse which is going to go left and right. And if the inverse goes left and right, the inverse will not be a function. When the inverse is not a function, sometimes you're asked to restrict the domain of the original function so that the inverse becomes a function. So let's talk about that. I have an original function which is y equals x plus 3 quantity squared minus 7. And I have switched out x and y and rearranged for y, and I end up with the equation at the bottom of the page. Y equals plus or minus root x plus 7 minus 3. And that's the red graph. And the red graph is clearly not a function because it will fail the vertical line test. If I want to restrict the domain of something like a parabola, which is there, or even an absolute value function, the x-coordinate of the vertex is going to be the key to solving that problem. When you take a look at the value of h in this function, f of x equals x plus 3 quantity squared minus 7, h is -3. That means the vertex is located at x equals -3. So two restrictions that will turn the inverse of the blue function, two restrictions that will create an inverse that is a function will be x is greater than or equal to -3 and x is less than or equal to -3. Let me show this to you. You'll have to look at the next page of this handout. There's the original, and this is not what's on the next page of the handout. It's going to change slightly. There is the original graph and there is the red graph. If I say, let's make x less than or equal to -3, what I'm telling you is that on that blue graph, we're going to get rid of anything to the right of -3. We're going to keep everything to the left of -3. So when I keep the left-hand side of that function, I don't get the reflection of the right-hand side. I only get the reflection of the left-hand side. So this graph at the bottom in red is now a function because it will pass the vertical line test. Incidentally, the equation of that is y equals the negative of the square root of x plus 7 minus 3. When I had the top and the bottom of that red graph, which was the inverse of the original with no restriction, the equation was y equals plus or minus the square root of x plus 7 minus 3. Similarly, I could make the restriction to the original graph x is greater than or equal to -3. Well, if I do that, then the left-hand side of the blue graph is going to disappear, which means the bottom of the red graph will disappear. So now again, the inverse is a function, and it turns out the equation of that is y equals plus the square root of x plus 7 minus 3. Transformations of root x. I'm not quite sure why it's important that we had a specific lesson on transformations of this function. I get that it's connected to some other things we learn in Chapter 2. However, what I'm going to tell you you should be able to do with this graph, you should be able to do with any graph if you know what that graph looks like. If you apply all of the parameters a, b, h, and k to the function f of x equals root x, that's what you get. That's the equation. So you should be able to look at the equation of a square root function that has been messed with by including a, b, h, and k and tell me everything about that function. Tell me the domain, the range, whether it points up and to the right, up and to the left, down and to the right, down and to the left. Any feature of the transformed function you should be able to do. And again, you really ought to be able to do that with any function that you're familiar with. This, however, is important. It's something that is new to this course and new to this unit. What does the square root of a function mean? Y equals f of x changes to y equals root f of x means that every point on the original function that's at x comma y is going to end up being x comma root y. This is the key to solving any problem where you're finding the square root of a function or you're finding information about the square root of a function. That's the mapping. Since you're taking the square root of y, then you're only allowed to do that wherever y is greater than or equal to 0. So any place on an original function that the graph is below the x-axis, which would be where y is negative, any place there, the square root function doesn't exist. And again, this is an opportune time for me to remind you, we're not doing math in this handout. You can go back, you can even pause the video here right now if you like, and go back and look at some specific examples from that lesson. Wherever the original function is above or on the x-axis, those will be points where y is positive or 0 and you are allowed to take the square root. There are invariant points associated with these functions. Since you're taking the square root of y, anytime y is 0, you're going to get an invariant point because the square root of 0 is still 0. Any place the y coordinate is 1, you're going to get an invariant point because the square root of 1 is still 1. Just to visually remind you of what these look like, that blue graph is y equals g of x. Y equals root g of x will look like the red graph. We have invariant points on the x-axis. There are 2 of them, and we have 2 invariant points where y equals 1 as well. The square root of a linear function looks like that. These are the 2 typical types of functions, square root and linear, that we've dealt with in class, but we've also dealt with other functions. And basically, if you're given the graph of a function and you're asked to sketch the graph of the square root, just start picking points and square rooting the y's, the y coordinates, and replotting them. Radical equations, just to remind you about radical equations are equations that contain square roots. You are not allowed to take the square root of a negative, and that means that this restriction must always be the case. If I have the square root of x plus 3 in the equation, then x plus 3 must be greater than or equal to 0, which means x has to be greater than or equal to negative 3. In this course, we're taught how to solve these radical equations graphically, because solving them algebraically was a Math 20-1 task. But I've told you in class, and we've seen in class, that sometimes it's just easier to solve these algebraically than it is to solve them graphically. Listen, I've taught you for as long as I've had you as a student, when you're solving equations, you are always trying to make things simpler. And getting rid of a radical is simpler than dealing with a radical. So in order for you to solve a radical equation, what you do is you isolate the radical, which means you move all of the non-radical terms to one side and the radical term to the other, and then you square both sides. What you're going to end up with is an equation that's not a radical equation. You're going to end up with a linear equation, or a quadratic equation, or a rational equation, but it will be an equation that you can solve. Remember that with radical equations, it's possible for you to get extraneous solutions, which means you've done nothing wrong algebraically, but one of the answers, or maybe both of the answers, or maybe none of them, but it's possible that an answer you get when you substitute back into the original equation does not work. Equations could also always be solved graphically, but don't do that if it's a written response question. That's Unit 1. And the questions in the big handout that I've created for you that deal with transformations and radical functions are 25 to 66 and 140 to 151. That leads us to Unit 2, which is actually, I believe, Chapter 3 of your textbook. I think it's kind of important that you recognize polynomial functions. Polynomial functions have terms. Terms are algebraic expressions that are added together. The terms have to have a base that's a single variable and an exponent on that base that contains a whole number exponent. They can also contain coefficients, but the coefficients must be real numbers. So, for example, h of x equals 2 minus root x does have terms. They do have variables. The variable is x, but root x is x to the half, and a half is not a whole number. F of x equals 3 to the x is not polynomial because the x is not in the base. It's exponential. When you take a look at p of x, which is the second to last one, the exponent is a negative number, which is not allowed for polynomials. So the only 3 polynomial functions are those ones I've given you. When you look at a polynomial function that is in expanded form, and I mean by expanded form that somebody has multiplied it all out if necessary to, for example, y equals negative 8x to the 6 plus 2x to the 4 minus 3x cubed plus 5x squared minus x minus 11. It's expanded out in that fashion. The constant term will always give you the y-intercept. The constant term will be the product of all of the constant terms of the factors. What I mean by that is if you were to take a look at a polynomial function that happens to be in factored form, and it's negative 3 times 2x minus 5 times x plus 1 times x minus 2. and I said, what is the constant term of that going to be if you expand it out? Well, you're going to end up multiplying a -5 by a 1 and by a -2 somewhere, and you're also going to end up multiplying by -3. So if I multiply those four numbers, which are the four constant terms in each of the four factors, whatever I get, which is going to be, it's looking like -30, will be the constant term of the polynomial, which will mean the y-intercept will be that -30. The leading term is the product of all of the highest degree terms. So for example, in my illustration here, if I said what will be the leading term, you would take the highest degree term in that times the highest degree term in that times the highest degree term here and here. And you would multiply those four highest degree terms together to get -6x cubed. So even though this is only going to be a cubic polynomial function, I still have four factors because one of the factors doesn't contain x. And that -3 times 2x times x times x, which is -6x cubed, will be the leading term when I expand it out. The leading coefficient is positive, then the right arm is up. If the leading coefficient is negative, then the right arm is down. If the function is even, which means the highest degree exponent on x is an even number, then both arms of the graph point in the same direction. They're either both up or both down. And if the function is odd, which means the highest degree on any value of x is an odd number, then the two arms point in opposite directions. Synthetic division is a useful thing to know how to do for the exam. It's used to divide a polynomial by any linear factor of the form x minus a. So for example, if I want to divide x plus 3, if I want to divide x cubed plus 7x squared minus 4 by x minus 2, then I set up a synthetic division template. And it's always going to look like this. What I do is in this position, I put the 0 of the divisor. I put 2. And if you take a look at the statement above this, when it talks about I'm dividing by x minus a, what I'm putting in that position is a. I'm putting the value of x that makes x minus a 0. I put in the middle 1 because there's 1x cubed, 7 because there's 7x squared. I need to include a 0 because there are no x to the 1's, and then I put a -4. And then I bring the first number down. And what I've got right here is what I've called in class, I've set up the playing field. Now I go to work. The first step is to multiply the 0 of 2 by the number below the line to get 2, and I write it above the line. Then I add those two numbers that are stacked. 7 plus 2 is 9. I take 2 times the 9. I add 0 plus 18. 2 times 18 is 36. 36 plus -4 is 32. And what I've discovered is that this is the quotient, which is the result of the division, but it represents x squared plus 9x plus 18. When you divide a degree 3 polynomial by x minus 2, you're going to get a degree 2 result. So I get 1x squared plus 9x plus 18, and this 32 is the remainder. And that's how you do synthetic division. I'm not so sure you're going to be asked to do synthetic division, although you might be, and it certainly can come in handy, but more often than not, you are asked to interpret the result of division and understand how all of these pieces fit together, which is called the division algorithm or division statement. When I divide that original polynomial by x minus 2, I get the quotient plus I get the remainder divided by the divisor. And you need to know that this is called the quotient. This, of course, is the remainder. This is the divisor. This is the divisor as well. Very often, that x cubed plus 7x squared minus 4 is simply called the original polynomial that we're dividing by. But there is a mathematical word for it. It's called the dividend. That is the division algorithm, or I prefer this. that if I multiply the quotient and the divisor and add the remainder, I get what I started off with before the division. So this is the dividend, that's the quotient, that's the divisor, and that's the remainder. I've highlighted the dividend because I believe, if memory serves, there was a typing mistake in your physical handout that I photocopied for you. I don't think the exponents on that dividend were correct. Remainder theorem. When a polynomial is divided by a binomial in the fashion that we've just done, the remainder is always the polynomial evaluated at that zero of the binomial. Just to remind you, this is what we looked at on a couple of the previous pages of this handout. So the value of a in our example at the top of the screen here is 2. 2 is the zero of the divisor. If I figure out what p of 2 is, that means I'm going to put 2 in for x in the original polynomial. It was x cubed plus 7x squared minus 4. Well, it becomes 2 cubed plus 7 times 2 squared minus 4. And if you check that out, that equals 32. That is the remainder when synthetic division is performed. The remainder theorem is not something that you would use to determine a remainder necessarily. You could use synthetic division. But any time you have a missing parameter, and we've gone through many problems like this, where you're given a polynomial and there's a parameter in it, instead of having 3x squared, it just says bx squared. And you're trying to find b, and you were told something like, when it's divided by x minus 8, the remainder is 20. You need to use the remainder theorem to solve that problem. Go back and take a look at the lesson on the remainder theorem and review some of those examples. If you do all 300 or so of those multiple choice numerical response questions, you're going to run into exactly what I'm talking about. The factor theorem goes one step further, and it says if p of a is 0, well, if I just back up for a second here, p of a is the remainder when you divide by x minus a. So if p of a is 0, that means when you divide by x minus a, there's no remainder, which means x minus a is a factor. I think this is very important, not just for you to figure out algebraically how to factor polynomials, and again, you need to look back in your lessons and review questions for examples of this, but it's important for you to understand that there's a connection between the zero and the factor. If the zero of the binomial is -2, which means an x-intercept of the graph is -2, then x plus 2 will be a factor. If 3 is a 0, or an x-intercept of the function, then x minus 3 will be a factor. And a seldom seen one, but, well, it's seldom thought of, it could be that 0 is a 0 of the binomial, or it could be that 0 is an x-intercept. That means the factor of the polynomial is x. I think it's very useful to be able to combine the factor theorem with synthetic division and this idea that's in the red box to be able to come up with all of the factors of a polynomial. What if you have rational zeros? What if you have zeros of 1/2 or zeros of 5/3? You ought to be able to work backwards and say that a factor that would give a 0 of 1/2 is 2x minus 1, and 3x plus 5 would give a 0 of -5/3. And again, you can use the relationship between those zeros or x-intercepts and the factors of the polynomial to factor a polynomial efficiently without using a whole bunch of synthetic division necessarily. Multiplicity. Multiplicity refers to how many times a specific factor or x-intercept or 0 appears in a polynomial function. So multiplicities that are even but greater than 0, because 0 is even, like 2 or 4 or 6 or 8, correspond to x-intercepts that are tangent to the x-axis. Multiplicities that are odd but greater than 1 correspond to x-intercepts that have what's called a point of inflection. So if I take a look at this graph, I've got a tangent point here. This is what a tangent point looks like. I have an inflection point here. That's what an inflection point looks like. I call this a clean point. It goes through with a clean passage, passes cleanly through. This would have a multiplicity of 1. This would have a multiplicity of 2 or 4, etc. And this would have a multiplicity of 3 or 5, etc. And more often than not in an exam situation, you're asked for maybe the equation of a polynomial function assuming minimum degree. So if it was a tangent point and you were assuming minimum degree, you would be using a multiplicity of 2. That multiplicity of 2 means that x minus 5 as a factor will be squared. The inflection point is at -1, which means x plus 1 is a factor. It will be cubed. The clean point at -4 means x plus 4 is a factor, and that means it will just be x plus 4 to the 1. Now, this is one of the rare cases in this handout where I go through a specific example because it's something that I really don't want you to get caught on. How do you find the equation of a polynomial function from either a graph or this information might be presented in a table or some other fashion? But how do we determine the equation of this polynomial function? Well, you have to build the function by looking at the factors, but you have to include a constant multiple of a. Well, just look at the fact that there's an inflection point at -1, which means there's a multiplicity there of 3, a minimum multiplicity of 3 because it's an inflection point. We also have a tangent point at 3, so we have a multiplicity there of 2. Most people, I shouldn't say most, when many people build this function, they say, well, the function must be y equals x plus 1 cubed times x minus 3 squared, and they pack it in and go home. They think they're done. Well, if they are, they're wrong because that is not the correct function. You have to include this constant multiple. Don't forget to include this when building a function. Now, how do you determine the value of that number? Well, it's found by the same strategy we use to find any missing parameter. Substitute in a pair of numbers that makes the equation true. Since this graph passes through 2, -26, when x is 2, y is -26, so I replace x with 2 and y with -26. I simplify that. 2 plus 1 is 3. 3 cubed is 27. -1 squared will give me 1. I'm saying -1 because 2 minus 3 is -1. So I end up with this. I end up with 27 times a equals -26. So a is -26 over 27. Don't forget to put that back in if it's a written response question. If you end it here, I can't speak to the state of mind of the markers on a diploma exam, but sometimes, as I've said in class, they're tired, they've been marking the same question for days on end, and they might just be instructed that if the student doesn't write the actual equation of the polynomial function, it's not good enough. It's not 2 out of 2 or 3 out of 3. So you do need to write that for an answer. Once you get that missing parameter, just take a minute, rewrite it with that missing parameter in place. And that is Unit 2, which deals with polynomial functions and equations. And in the handout, the big one with 300 and some odd questions, numbers 115 to 138 are problems that deal with polynomial functions and equations. That's it for the first part of this video. Talk to you later.